Well, let's take a look at number 18 in section 2.1. It's an even problem, so the answers I don't believe are in the back of the book. For questions 15 through 18, you're given matrices with a variable, and this variable, I don't know if you've seen this Greek letter before. This is the lowercase Greek letter lambda, and we'll be using that quite a bit when we look later on in the semester at the eigenvalue problem. But the matrix here is 3 by 3 in number 18, and we're to find the values of lambda for which this matrix, its determinant is 0. Remember, the determinant is a real number associated with every square matrix. So we have to find the determinant, and for a 3 by 3, we're going to use cofactor expansion. Now, where would you do cofactor expansion? You can go along any row or any column. Well, you're going to choose the row or column that has the most zeros in it, because that makes the calculations much easier. So you do not want to do this along row 1 because there's 2 non-zero entries in that row. However, row 3 or column 3 would be the choice. And so I'm going to do it along row 3. So this entry times its cofactor, I don't even care what its cofactor is because 0 times anything is 0. This entry times its cofactor, again, 0 times anything is 0, so I don't care about that cofactor. But I do have to worry about the last one, lambda minus 5 by its cofactor. What is that? Well, it's -1 to the row number is 3, column number is 3, 3 plus 3, -1 to the 6th times its minor. Of course, -1 to the 6th is just +1. Remember, the cofactor is either positive or -1 times the minor. Don't forget this. I see this forgotten a lot. Here, it doesn't matter if you forget because it is 1, but sometimes it's -1 and that will throw you off. So remember the pattern of signs, right? By entry, positive, negative, positive, negative, positive. So this is +1. And what's the minor? It's the submatrix found by removing the row and column that the entry lambda minus 5 in. So this 2 by 2 matrix in the upper left-hand corner. So I'm finding the determinant of that. And the determinant of that is this product, lambda times lambda minus 4, minus 4 times -1, minus -4. So be careful here with sign numbers. Minus -4 becomes +4. I distribute this lambda through. I get lambda squared minus 4 lambda. And now I can factor this. Okay, if I couldn't factor this, if it was prime, I would use something like the quadratic formula or completing the square to find the values of lambda that make this 0. But since it factors, it's a perfect square trinomial, lambda minus 2 quantity squared. Here I have completely factored the determinant, and I can clearly see that the determinant is going to be 0 when lambda is either 5 or 2. So those are the two values of lambda that make the determinant equal to 0. Now, there's lots of ways you can check this. One is, simply plug back in these values to the original matrix and make sure it's true that the determinant is 0. Well, if lambda is 5, then clearly this goes to 0, and clearly the determinant is 0 because we have a row or a column of all zeros, and cofactor expansion along that row or column will give an answer of 0. So it's obvious that 5 works. But what about 2? I'm going to replace lambda with 2, and I've done that down here. If I replace that in, I get this matrix. Okay, so for instance, 2 minus 4 is -2. Lambda's 2, and so on. So I just do that calculation. Now I find the determinant by cofactor expansion again along this row. So I've got 0 for that one, 0 for that one, -3 times 1 times its minor, right, which is that up there. But when I calculate this minor, I get -4 minus a -4. Well, that's 0. And so the determinant is 0 as we expect it to be. So you can check and confirm this, and that's helpful. For instance, in this problem where it's even numbered, there's not answers in back of the book. How do we know we did it correctly? Well, check. So many of you need to make sure that you check your answers. It's an important thing to make sure your answer is reasonable, not just in linear algebra, but in any problem in life. Okay? So hopefully this is helpful.